Okay, so we are ready to start chapters 18 and 19. I'm grouping these chapters together. You can read through them as you study through your textbook. And this chapter is, these two chapters are really all about ultraviolet visible molecular absorption spectroscopy, short UV-vis spectroscopy. And in this chapter, for the most part, we are going to be considering molecular spectroscopy, which is more or less light absorption and or emission by molecules. And that's very different than chapter 20, as we'll find. Chapter 20 is going to deal with light absorption and emission by atoms. And I want to establish that difference because sometimes I think students get confused that everything gets thrown together in their mind. But there's really two different branches of spectroscopy that we're considering and use very different equipment for both. First, we're going to consider spectroscopy of molecules. So as always, I put the slide up on Blackboard. You can find them in the same folder that you're finding this video in. Download the slides, follow along, take good notes in your notebook. We've got lots of key terms that we want to know the definition to, and many different learning objectives here for this particular set of chapters, okay? All right, with that said, let us get started. So I wanted to start with a review of the basics of electromagnetic radiation. Now, of course, we know visible electromagnetic radiation, the light that we can see as light, okay? But there are many other regions of the electromagnetic spectrum that can interact with matter. We just can't see it, right? So what is this electromagnetic radiation? Well, it's believed to be an oscillation of the electrical and magnetic fields, okay? Now, this oscillation of these two fields occur at right angles or 90 degrees to one another. And you can kind of see that in this picture up above, okay? The blue is supposed to be the electric field, and that oscillates, right? The magnetic field oscillates in a direction that's basically at a right angle to the electric field, okay? And these two fields are basically coupled, and this can propagate through space. And this is our model for the electromagnetic radiation. Now, because we treat electromagnetic radiation as having certain wave-like properties, we can then use this equation, which I think you've all seen before, right? C is equal to lambda times nu. This interconverts between C, it's called the speed of light, and that's usually given in meters per second for scientific purposes, and C is equal to 2.99 times 10 to the 8th meters per second, okay? So quite rapid. The light moves, so that's our C, our speed of light. And that's always equal to two numbers multiplied by one another. Now, the funny looking V is our frequency of our electromagnetic radiation as measured in hertz, which also has units of cycles per second, S to the -1. And our lambda is called the wavelength. That's measured in distance units. For use in this equation, we're going to use meters for that, okay? Now, the wavelength of the wave is the distance required for one complete oscillation. And that can be anywhere from picometers to tens, hundreds of meters, okay? The electromagnetic spectrum spans a huge range of wavelengths. And that's important to understand because not all electromagnetic radiation has exactly the same properties because the wavelengths are different and correspondingly the frequency is different. Now look at this equation real fast, right? Just in case you forgot. Think about the frequency, the funny looking V, as it relates to wavelength. If the frequency of a wave, let's keep it Q, if that goes up, what must happen to the wavelength? The wavelength must go down. Reason being, you multiply them together, you've got to get that constant C, right? So wavelength and frequency are always inversely proportional to one another. Now, we also learn about this equation as it relates to electromagnetic radiation. And this is what I like to call, I guess, the photon energy equation. Because what this equation does for us, E is equal to h nu, is it allows us to compute the energy, which is the E term, of a single photon of light. One photon. Now I use this word photon, didn't I? Photon is basically, the idea behind it is like this fundamental packet of electromagnetic radiation. The idea is electromagnetic radiation comes quantized in these packets that we're just going to call photons. And we can compute the energy of one of these packets or photons using that equation. E is the energy. Now, to do that, we have to multiply two numbers together. Of course, H is referred to as Planck's constant. It's just a number. Whenever you have a constant or a number in your equation, it's kind of useful, right? Because if you just kind of remember that constant, can quickly plug in a number, plug and chug for calculations. So H is equal to 6.62 times 10 to the minus 34, and it has units of joule seconds. So E, when you use that number, will be computed in joules energy. And then we've seen this funny looking V before. That is just our frequency as measured in hertz or cycles per second, okay? Now, if you multiply the frequency times Planck's constant, you get joules of energy. So the equation in terms of units is internally consistent. This allows us to compute the energy of a single photon or single packet of electromagnetic radiation of a certain frequency. So what does this mean? Okay, as frequency increases, the energy also increases. They're directly proportional, right? As the funny looking V frequency goes up, it gets bigger and bigger and bigger, energy increases. But on the other hand, if our wavelength goes up, by virtue of this equation, doesn't that mean our frequency gets smaller? So as wavelength increases, energy decreases, inversely proportional, okay? So this is kind of a review or some of the basics of electromagnetic radiation. And of course, if we want to, we can be very mathematical with these equations. We can compute energy of a photon. I think you've seen those types of problems before. So they're in your textbook if you want to review the first few pages of chapter 18. But I'm not necessarily going to go through a problem, but hopefully you know how to do that, because you could see a problem on the quizzes and also in the exam. And I think I'll probably give you a quiz problem today based on that, so you can review it just a little bit. But it's pretty easy, right? It's just algebra. All right, so moving on. What we really want to get at in this chapter is how light interacts and affects molecules. Turns out it can have some pretty profound effects, but the trick is the effect light has on a molecule depends upon what the frequency or energy of our light actually is. So because the electromagnetic radiation has many different types of or classes, if you will, of radiation, we can have lots of different interactions. All right, so right here in the middle, we see names of different types of electromagnetic radiation. These are different classes or categories. Now, what's most familiar to us is right here. If you can't read that, it says visible sideways, okay? That's the light that we can see with our eyes, the visible radiation. Visible radiation, you can see that with our eyes. Now, it's like the Roy G. Biff spectrum, okay? Now notice that's only a tiny little sliver of the entire electromagnetic spectrum, and that's even true. This scale is not even, this x-axis is not even drawn to scale. But if we actually zoomed in on just the visible spectrum, what we would see is that the visible spectrum encompasses wavelengths, and this is nm or nanometer units, but it encompasses wavelengths from about 400 to about 700 nanometers. That is our visible range. This is the light that our eyes can see. Now, about 400 nanometers is a violet color. Once you get to about 450 or 460, you're in the blue. About 520, 530, it's green. Green light, okay, we perceive that as green. Once you get up about 560, 565 or so, the light starts turning yellow. It quickly goes through orange around 590. And this whole region here between 600 and 700, I usually always perceive that as red, okay? So different colors have different wavelengths and correspondingly different frequencies, but we can only see this tiny little sliver of visible light. Now, there are many other regions, like for instance, the ultraviolet or UV region, is to the left of our visible. And what does that mean in terms of frequency or wavelengths? Well, ultraviolet rays are shifted to the left here, so they actually have smaller wavelengths than visible, but they have higher frequencies than visible. So UV radiation is more energetic than visible. Waves which are at the left of our plot are very high energy, and those over here on the right are very low energy, okay? Moving further left, we have our X-rays. You probably heard of X-rays when you go to the doctor, you think you have a broken bone or something, right? They give you an X-ray. Those electromagnetic waves have wavelengths even shorter than ultraviolet, below about 100 nanometers, okay? And even more energetic than that is our gamma rays. These have exceedingly small wavelengths, less than 10 to the minus 11th meters, and very, very high frequency and high energy as a result. Gamma rays are usually produced by nuclear decay events, things like that. Not so great to be around those. Now, on the other end of the spectrum, the other direction from visible, we have infrared or IR. These typically have wavelengths measured in the micron region. To the right of that, we have our microwaves, greater wavelength. And then we have our radio waves, way out here, which have the highest wavelength of any wave on our scale. And of course, the gamma rays have the shortest. Radio waves, they might have wavelengths in excess of 10 meters, even hundreds of meters. Huge, huge, huge wavelengths, okay? So we have this spectrum, and frequency and wavelength are inversely proportional according to that equation. Now, how do these different types of waves affect molecules? That's kind of our next question, right? They affect them in very different ways. Okay, now let's talk about the gamma rays and the X-rays first. Turns out that gamma rays and X-rays are what's called ionizing radiation. Okay. Basically what that means is that X-rays and gamma rays contain so much energy in a single photon that they can actually break chemical bonds. They can break chemical bonds. They have so much energy. Now, if a molecule interacts with a gamma ray or a X-ray and bonds are broken, I mean, this destroys the molecule, right? Now, obviously, you could imagine that it's not so good for you, your health, to be around ionizing radiation. That's why we try to ignore it, right? The dentist or the person in the physician's office that gives you the X-ray wears that lead shield, right, to protect themselves from the X-rays. And oftentimes they have little badges that counts their exposure or tracks their exposure. Because we don't necessarily want to be near this ionizing radiation because it's so energetic, it'll break bonds, okay? That could cause all sorts of genetic problems, right? We don't want that. What about then the UV and the visible? We're going to group these two together. And the reason why is because ultraviolet and visible transitions can carry out what's called electronic excitation or electronic transitions in our molecules. Basically what that is going to mean is there's going to be two allowed energy states, the low energy state and the high energy state. And a UV photon or a visible photon basically can take our molecule from the low energy state and the high energy state. There's an energy gap between them, but that can be bridged by our photon energy. And if that happens, we can move the electron from the lower energy state to the higher. That's actually what we're doing here, is we're taking an electron and we're moving it from the low energy state to the higher energy state. UV vis photons are great energy to do that for us. It just so happens that Molecules have certain energies to bridge that gap, and those energies correspond with UV vis photons, right? Now, on the other hand, we have our infrared or IR waves. Many of you have taken organic chemistry before, and in organic chemistry, you actually study infrared spectroscopy, don't you? And you can assign certain bands in the spectrum to different functional groups, and that's kind of a common thing to do. It's actually pretty useful to try to figure out the structure of molecules. Well, this type of electromagnetic radiation affects vibration in molecules. So if this is nucleus 1 and this is nucleus 2, those atoms are connected by a bond, aren't they? As it turns out, chemical bonds are oftentimes modeled like a spring. You know, think like a slinky or a spring, right? That's what I'm kind of talking here. It can stretch, it can contract, right? So, that type of spring. And there's mass 1 and mass 2. And basically this bond or the distance between the nuclei is not fixed. It's not always the same, but it actually changes dynamically as the bond vibrates along the bond axis. Now, it turns out that infrared radiation is just the right frequency to couple to that type of vibrational energy. And sure enough, infrared can be absorbed and used to change the vibrational nature of molecules. So IR spectroscopy is vibrational spectroscopy. Now, if we get way out to the microwave, what we're actually studying there is rotations of molecules. It turns out if we have a bond, like something maybe like an HCl, okay, where we have a polar bond, there's a partial negative end and a partial positive end. As that molecule rotates around in space, okay, that rotation creates an oscillation of charge or electric field, and that can couple with microwave radiation. It's the right frequency to couple with it. And in doing so, microwave radiation is absorbed and can affect the vibrational levels. So this is the type of different ways that molecules are affected. Now, chemists give this type of interaction a kind of a special name. They're called transitions, okay, transitions. So we might say the molecule undergoes an electronic transition for ultraviolet or visible rays, or a vibrational transition. This is a way to say that the molecule interacts with light. Okay, so lots of different frequencies, lots of different wavelengths, and each type of electromagnetic radiation does something different. So I'd like you all to be able to order the electromagnetic spectrum from high frequency to low, from high wavelength to low, and from high energy to low, and vice versa. And also, I want you all to know approximate wavelength ranges for these different color lights. And we should know that 400 to 700 nanometers is visible. And ultraviolet, I'm going to say ultraviolets from about 200 to 400 nanometers. Some people sometimes say 190, the extent of the ultraviolet, okay? This is UV, and this one is visible. Okay, so know that, because that's just like information that people just kind of assume that you know. Another thing to know is these types of transitions. So know that infrared spectroscopy carries out vibrational transitions, or microwave corresponds to rotational. Know the ionizing radiation breaks bonds in molecules, right? Know that UV and vis undergo these electronic excitations. So that's the kind of thing that I'm looking for you to understand for this. This is kind of like basic chemistry knowledge, all right? Now, if we're going to do UV vis spectroscopy, we talked briefly about what types of transitions may occur in molecules. But what I'd like to do now is get more quantitative and say, oh, well, okay, if we're going to use this method, what do analytical chemists want to do with it? Well, there's actually quite a few things. I mean, one is to get information about the molecules in question. And you saw that with IR spectroscopy and organic chemistry, didn't you? You could figure out structural cues from the IR absorption spectrum. But another thing that we can do with these types of measurements is actually quantify the amount of material present. So to do that, we need to define a few terms and understand them, and then figure out how we're going to use them. So something called Beer's law. So let's start at the beginning, right? Let's just say that we prepare a sample which absorbs light at a particular wavelength. We usually make measurements at a specific wavelength when we're doing these sorts of discussions. So what I'm going to do is I'm going to take a light bulb. This is my light bulb, okay? I'm not a very good artist, but you get the idea, right? That's my light bulb. And it gives off light of a particular wavelength. Now the intensity of that initial beam is I0. I call it the incident beam because it's incident or directed towards my sample, which is this yellow box. Now, if the sample absorbs a portion of the light incident upon it, what the light which escapes on the right side over here will be lower intensity because some of the light will just simply be removed from the beam by the sample. Now, if that's the case, I can quantify in a very simple way how much light was lost. I can derive a term or define a term called the transmittance. And transmittance is easy to understand. It's just the ratio of I, the light which escapes, divided by I0, the light which was incident upon the sample. So the transmittance is a number then between 0 and 1. If all the light makes it through, the transmittance would be 1. And if none of it does, if it's completely dark, the transmittance would be 0. But usually our samples lie somewhere in between, all right? Now, that term is very easy to understand. And if I want to get fancy, I can even decide to define a percent transmittance, which is just T times 100 to express it as a percent, right? Another useful equation here, right? But here's the thing. When chemists started using that term, T, transmittance, which is easy to understand, they quickly realized that transmittance was actually not linearly proportional to the analyte concentration. It was actually like a logarithmic relationship. So they decided then to maybe derive a term related to the absorption of light that is linear with analyte concentration. Okay, so that allows us then to discuss absorbance, which is given the symbol A in these equations. Okay, and absorbance and transmittance are actually definitely related, and they're related through this equation. So we'll want to highlight that equation in your notes. We'll want to know how to use this, okay? Absorbance, by definition, is minus base 10 log of the transmittance. Now that T right there is the one between 1 and 0, 0 and 1. Absorbance can also be computed by 2 minus the log of the percent T. These equations are basically interchangeable. So if we know the transmittance, I can compute the absorbance. All right, and that's important, an important skill. Actually, I'll give you some sample problems in your quiz today as well that require you to do that. And you could expect to see that type of thing on your next exam, interconversion between absorbance and transmittance. But with a term now that is linearly proportional to analyte concentration, we're kind of off and running. So what can we do with this idea of measuring light transmitted through a sample? It turns out we can do many different things. Okay, let's look at this slide now. Now, what the purpose of this slide is to define to you, if you didn't know, what an absorption spectrum is. And to be really sort of forward, an absorption spectrum is this plot. It's a plot of absorbance versus wavelength, okay? And wavelength is often expressed in nanometers if we're doing UV vis spectroscopy. Absorbance versus wavelength. So why make this type of plot? And how do we do it? Well, first off, we're going to use a device called a spectrophotometer. And that spectrophotometer is going to have the technical ability of being able to scan or change the wavelength. We can, there's usually a range of wavelengths. Maybe it's 400 to 700, maybe it's 200 to 700 or 200 to 1,000 nanometers, but we can actually change or scan the wavelength that we apply to our sample. And the reason why we do this is because molecules do not absorb all wavelengths equally, not at all. The absorption at a particular wavelength depends upon the electronic structure of the molecule in question. So different molecules have different absorbances, or different absorptions at different wavelengths. Now the absorption spectrum is simply a way to make sense of all this. Because what we do is we go to a lab and we actually measure the absorbance of a sample as a function of wavelength. And then we plot out the results, okay? So these different plots here on this graph are all absorption spectra. There's like 5 different, because they're different concentrations. The number right here, 4, 8, 12, 16, 20, those are actually the concentrations of potassium permanganate in parts per million. Okay, so you can see that the absorbance increases as concentration increases as well, and it does so linearly. We'll get more on that in a few minutes, but what we want to do right now is learn why this absorption spectrum is interesting to us, okay? Well, the reason why is because it provides a graphical depiction of where this molecule absorbs light strongly, okay? And that's what I want you to understand. Because we plot absorbance versus wavelength, I can quickly come into this plot and locate the peak absorbance, which is right there, right? And it looks to me that occurs somewhere around 525 nanometers wavelength. So that wavelength, 525 nanometers, is the peak absorption by this material. Now, does it absorb at other wavelengths? Yeah, it absorbs over here. And then down here, it kind of starts approaching zero absorbance, doesn't it? So it absorbs at other wavelengths. This is the peak wavelength, it's 525. So we call that peak wavelength lambda max, or sometimes the analytical wavelength. And the reason why that is because usually the analyst will choose to make their quantitative measurements right at that wavelength. Because, well, the stuff just absorbs light strongest there. I can get most sensitive detection as a result. So the absorbance spectrum is nothing more than a plot of light absorbance versus wavelength. It gives us information as what color or what wavelengths of light is successfully absorbed by the molecule of interest. And that's why chemists use it, okay? Now, we got to get quantitative. Remember I said that absorption was linear with concentration? Well, the Beer-Lambert law is a mathematical relationship which formalizes it, okay? Now, the Beer-Lambert law ultimately is going to be this equation, and this is what you kind of need to remember, okay? The rest of it's just a mathematical derivation at the bottom, and I'll talk about here in a second. But what the Beer-Lambert law says is that the absorbance A is equal to epsilon, the molar absorptivity, times the path length times the concentration. If you multiply path length, concentration times the molar absorptivity together, you get this absorbance that we're going to talk about, okay? Now, what are all these terms? Well, in a nutshell, I'll kind of summarize first, and then I'll talk about the mathematics at the bottom. The path length, measured in centimeters, is just the distance the light traverses through the sample. Usually for a lot of UV-Vis molecular absorption, that's going to be 1 centimeter. That's kind of a common distance, okay? But it's the distance the light beam has to travel through the sample. And the concentration, here it's molarity, right? This is the analyte or the light absorber concentration in molar units. It doesn't have to be molar units. It actually can be other units besides molarity. Molarity is, in fact, however, common. Now, if you use molarity, epsilon is your molar absorptivity, with units of liters per centimeter per mole. Now, what is molar absorptivity? Well, this one is, I like to say it's kind of like a fudge factor that describes how well a molecule absorbs light at a very specific wavelength. Molar absorptivity is wavelength specific. You change the wavelength, well, the molecule may absorb light differently, and because of that, we need a term that describes the wavelength, the wavelength dependence of light absorption, basically. So this molar absorptivity does that for us. It's a number that just describes how well a molecule absorbs light. The bigger the molar absorptivity at a specific wavelength, the better the molecule is at absorbing light. All right, so this is our Beer-Lambert law relationship. We'll see problems based on that. Now, the cool thing about the Beer-Lambert law is like we learned about this and it just kind of rolls off the tongue. Everybody remembers A equals EBC, okay? But the super cool thing about it is it actually can be derived mathematically. And that's actually what's shown down here if you're interested in that, okay? So we start with this very simple model of a sample cell and an incident beam. Now that incident beam is going to traverse through the sample cell, but we're not going to first consider the entire sample cell. We're just going to consider a very, very, very thin layer at the entrance of the sample cell compartment, which is usually called or referred to as a cuvette. Now that thin layer is going to have a thickness dB. Later, I think I'm going to call that dz, okay? Well, actually, at first I call it dz, and then I'll switch back to dB, but it's just the thickness of the layer, okay? Now, what we can do is we can come up with an expression, a mathematical equation, to relate the light absorption from the beam normalized back to I0. So this ratio on the left is basically the fraction of light which is absorbed, okay? The fraction of light which is absorbed. And that's going to be equal to this. Now, let's talk about that for a second, okay? Now, in this very thin layer, here's how I'm going to model it. I'm going to draw this gray box. Now, that gray box has a certain area, doesn't it? And I can measure that area. Maybe it's 1 centimeter by 1 centimeter, it'd be a square centimeter, right? Or a centimeter squared. But there's a certain area associated with that gray box. This is a surface area, right? Distance squared units. So what I'm going to do is I know that this sample of light, it absorbs light. So why don't I model certain spots, and these are going to be these dark spots, the black spots, certain spots in that layer as being basically perfectly absorbing. Those are those dark spots. And I'm going to basically build this model that says, okay, just by random chance, if a photon hits one of those dark spheres, it will be absorbed because they're very, very absorbent. However, if a photon hits the gray area, it just passes through this thin layer. And that's my model, basically. So if I want to figure out the fraction of light that's absorbed, it's easy. Well, if I could find the area of all those black dots together and divide by the total area, I'm in business, right? So the area, or the sum of all the black dot area divided by the gray area, hey, I got my fraction of light that's absorbed. And really, it's as simple as that. That's what I'm going to do right there. So A is nothing more than the gray area. And then the numerator of this fraction right here is going to be the surface area of these black dots, basically. Now, it's going to be a little bit more confusing. We got to figure out how we compute that. So let's go through that, okay? So what I'm going to do is I'm going to multiply a term called sigma, which I'm going to refer to as the absorption cross-section here. It's going to have centimeter squared units. I like to think that in my physical model here is basically the area of a single black dot. I could compute the area of that, right? A single black dot. That's my sigma, absorption cross-section. And what I'm going to do is I'm going to take that absorption cross-section and I'm going to basically multiply it by the number of dots in that layer. Now, obviously in the equation, it's not the number of dots. It actually will derive that, or we'll figure that out. But you see I have the n times the a times the dz. Why is that? Okay. Well, n is the concentration. It's basically the number of absorbing dots per unit volume, per milliliter or centimeter squared cubed here, okay? And I'm going to take that and I'm going to multiply it by dz times a. Now, dz is that layer thickness. It's the same as dB, just a different level, okay? Letter, but layer thickness. I'm going to multiply that layer thickness times a, the gray area. Now, think about what I get when I multiply those two together. I get a volume. So I'm going to take that volume, I'm going to multiply it by the concentration, the number of dots per unit volume, and when I work this math, n times a times dz, what that works out to is the number of black dots inside my volume under question. The number of light absorbing dots within the volume. I'm going to take the number of dots and I'm going to multiply it by the cross-sectional area of all the dots. Well, I'm going to multiply the cross-sectional area, sorry, of one dot And once I do this mathematics, think about what that yields. In the numerator, that's the area of all the black dots. So I take the area of all the black dots together, integrated together, right? Or added up. And I divide it by the area shown in gray. And that gives me this ratio, because I assume my dots, if light falls on it, it is a perfect absorber, basically, okay? And it's as easy as that. Now notice in the mathematics, A appears both in the numerator and denominator, so I can cancel that out and get rid of the denominator. And what's left is sigma times n times dB, where dB is my layer thickness. And that's as easy as that, okay? All right, so I've derived an equation for the fraction of light that's absorbed. Now, if I want to, I can clear this denominator by multiplying by both sides, which yields this equation right here. Now that describes the intensity of the light that's been absorbed, basically. So I just take my fraction of light that's absorbed and multiply it by the incident intensity to get that result, right? Simple enough, right? No big surprises there. So what I'm going to do then is let DI represent the change with respect to the incident intensity, how much the incident intensity changes as the beam traverses the sample through a layer thickness, which I'm going to refer to as dB. Notice how I switched dz to dB. Z is really just a typo, okay? It should always be B in this case. Okay, so as the sample traverses this distance dB, this very, very thin layer at the end of my cuvette, DI tells me the change in intensity. Now that change in intensity caused by absorption should be minus I absorption, minus this term, minus because the light's removed. So consequently, I can say that that change in the incident intensity is equal to that term right there, okay? Which is just the negative of this. I multiply by -1, basically, okay? Then what I'm gonna do is I'm gonna take that change term DI, I'm moving over here now, okay? The change term DI divided by I0 equals negative sigma NdP. I'm going to integrate from I to I0 to I. Know what that is, and then from 0 to B. So basically what I'm going to do is I'm going to add up all of the layers present in this cuvette. Okay, so remember we've been considering this very thin layer at the entrance to the cuvette. This cuvette might be a centimeter thick, and this thin layer is kind of a theoretical construct, right? But it's a very, very thin layer, and there are many of these layers which are essentially identical across this 1 centimeter difference. So I have to add them all up, and in calculus that's the integration, right? So I'm going to integrate from 0 to B. I'm going to add up these infinitely thin layers, or very, very thin layers. Mathematically integrate, that's the step that's shown here. And when I do that, I yield this. Okay, and again, you don't need to know the details of this. It's just kind of going through and explaining the process. Some of you might be into that, others maybe not, okay? But you get this. Natural log of I over I0 is equal to negative sigma NB. Okay? Now, this equation is starting to actually already kind of look like our Beer-Lambert law, and maybe you don't see that yet. So what I'll do is I'll rearrange it and solve for I, the light intensity, and that's equal to I0 times E, the base for natural logarithms, raised to the negative sigma NB. We had to introduce that E because we took the anti-log, converting from the equation above. And what we can do with that then is arrange this equation by solving for I over I0. Now, I over I0, remember, I0 was our incident intensity. What comes out the other side is I. So that ratio is nothing but our transmittance. And the transmittance equals E, the base for natural logarithms, raised to the negative sigma NB. All right. Now, from there, what we are going to do is we're going to take the natural log of both sides to get rid of the E. So when I take the natural log of both sides, this comes down, and I'll have to have the natural log of t because I took the natural log of that side as well. Now, nothing wrong with that equation. It's just sometimes we like to work in base 10 logs rather than natural logs. So why not do a conversion from natural log to log? Unfortunately, there's a really easy way to do that. There's this relationship between natural log and base 10 log, where you have to multiply the base 10 log times 2.303. Okay, that's where this number comes from. It's just a conversion back to log instead of ln. So log transmittance times 2.303 is equal to this, basically, which then equals this. So because of that, I can then take negative log of t and set that equal to sigma and b divided by 2.303. Now, what if I take this sigma, my absorption cross-section, and divide it by 2.303 and call that the new constant? I'm going to call it epsilon. So epsilon is equal to sigma divided by 2.303. I'm just making a new constant, okay? And I'm plugging that in the equation down there at the bottom. Now, what's the significance of that? Well, negative log t just comes down. So the negative log of the transmittance is equal to epsilon times n times b. This is just a spurious mark, okay? A few slides ago, didn't we decide that A, the absorbance, is equal to negative log of t, or 2 minus the percent t? So negative log of t, well, that's my absorbance. And I came up with this new number, epsilon. This is just my cross section divided by 2.303. And O was N. It was my concentration. And B was my path length. Because remember, we started off with dB being that infinitesimal thin layer. And then we integrated to add up all those layers that ends up yielding this B, the total path length. Notice that's exactly the same as our Beer-Lambert law. Epsilon, here I used C for the concentration, but it's the same thing, right? Times path length. So it's really quite interesting, but you can actually derive this Beer-Lambert law just from this pretty simple model, okay? That's kind of when I go through that. It's sort of interesting to me, always been sort of cool. Now that we're on with this Beer-Lambert law, A is equal to EBC. What can we do with it? Well, we can do all sorts of quantification of analyte. Because the absorbance of our light absorbing substance is proportional to the analyte concentration, linearly proportional. So if I make a plot of absorbance as my y versus concentration of my x, what I can see is that the slope of the relationship of these two variables is m. From the equation, that's equal to E times B, epsilon times path length, molar absorptivity times path length. Now, fortunately, often I'll say, the path length is 1 centimeter in this experiment. It's just kind of evolved to be a typical path length. It doesn't have to be, okay, but it just oftentimes is. And you always want to experimentally verify that, but it's common that we use a 1 centimeter path length. And if that's the case, boy, that's really convenient because you could plug a 1 in here for B, and the slope of that line gives you information about the epsilon. Now, if you change the wavelength, the slope of this line will change because the epsilon will change, okay? But for a particular wavelength, absorbance and concentration are linearly related. So what you do to derive or figure out this relationship is you go in lab, you make yourself a blank, and then you make yourself several standard solutions of increasing concentration. You measure each of them on your spectrophotometer, and then you just make a plot in Excel. It's as simple as that. That's your calibration line. So this type of plot is given a special name. It's called a Beer's law plot or Beer-Lambert law plot sometimes, okay? And all it is this plot of absorbance versus concentration. It's sort of like our calibration curve for this type of experiment, basically, okay? Beer-Lambert law plot. And it shows the linear relationship between absorbance and concentration. Now, I keep mentioning this linear relationship, but sometimes things go wrong. Sometimes we plot out absorption for concentration, we'll see a linear range, but then the plot might level off. It's actually sometimes commonly observed. If you go to a high enough concentration, you actually generally always see this, okay? So why does it go nonlinear? Well, why does this happen? So I want you to know that it can happen, first off, and don't be surprised if you see it in your professional dealings. But why does it happen? Or what are some reasons for it, okay? There's actually a number of different reasons, and these can, what's responsible can vary depending on, your particular analyte, your particular experimental conditions under study, okay? But these are just some things that can go wrong. So one is some small deviations, maybe even large deviations, in the molar absorptivity can occur at very high concentrations of analyte or perhaps at high ionic strengths, because then analytes don't behave independently anymore at very high concentration. The analytes might start to have crosstalk, right? Molecular crosstalk or interactions, if you want to think about it that way. And even at high ionic strengths, that can happen. Now, if that starts to occur, then maybe the light absorptive properties of that analyte will change. And if that's the case, epsilon changes, and that could lead to nonlinear plots. Another thing that can go wrong is scattering of light due to dirty samples. Now, you might have fibers, particles in your samples, lots of possibilities. It could be an emulsion, something like that, right? Well, those dust particles or fibers will scatter light. And your spectrophotometer really has no way of telling the difference between a loss due to scattered light or a loss due to light absorption. So your spectrophotometer is just going to measure the light lost. And if you've got a dirty sample, well, it's going to measure that, okay? And that can lead to some quantitative errors or difficulties. So you should always filter your samples, remove particles and fibers. Another thing that can go wrong is fluorescence or phosphorescence. Now, we haven't talked about what this is, but this is actually an emission spectroscopy. And in emission spectroscopies, what actually happens is the molecules of interest will absorb light, but they actually then glow or give off light. They emit light to the surroundings. And that light can be collected by your spectrophotometer and sensed, and that can cause all sorts of weird quantitative issues as well. Refractive index might change at high analyte concentration, and losses, optical losses due to refraction would change accordingly. If you've got some kind of chemical equilibrium system, that can sometimes shift due to changes in concentration or pH or some other condition. And then the last two are sort of instrumental related. One is use of non-monochromatic radiation. So I use an important word here, monochromatic, which literally means one color. Remember earlier I said that we usually do this absorption or transmittance experiment at a particular wavelength, and we make measurement at a particular wavelength. That's actually super important for absorption spectroscopy. In fact, Beer's law won't be valid if you do not meet that condition of monochromatic or single color radiation. And the reason why is because molecules do not tend to absorb light at all wavelengths equally. So what ends up happening if you use very broadband radiation, say white light, which is lots of different colors of the rainbow, or really all different colors of the rainbow, what happens is that the wavelengths which are absorbed well by the molecule will basically quickly be attenuated or lost. But all the other wavelengths which are not absorbed will simply just pass through the sample and hit the detector, producing an electrical signal. So once the wavelengths that are absorbed are gone, there will be no further change in absorbance noted in such samples because the other light just passes through unaffected. So because of this, you really always want to use monochromatic radiation when you're doing these measurements, light of one color or narrow bandwidth, okay? The last thing that can go wrong is stray light. Typically, spectrophotometers are designed to eliminate light from the outside world, the room, getting into the light detector and producing a signal. because obviously light from the room that you're working in, you don't want to detect that. It has nothing to do with your analyte whatsoever. But in some cases, um, a dark signal or stray light can be really important to your signal. And think about a case where your analyte concentration is really quite high, a very high analyte concentration. Now, because of that, absorption will be high because absorption and concentration are directly related. Well, what if absorption is 3, 4, 5? It's a very, very high absorption. And what that means is at the wavelength under study, basically all of the light is being removed from by the sample. There's none making through the sample. Well, if there is any stray light present, even small amounts, that will be indicated, and that's going to cause huge quantitative issues, okay? So stray light can sometimes cause problems, right? So these are some of the things that can go wrong. All right, so I think it's time to end this video. Appreciate your patience, and we'll pick up more in the next.